say
it's n equal 3, by the way.
n equal to 3. No, this is n minus 1, and I said n equals 4. Huh?
Doesn't matter.
No matter.
Look up, n is from 0 to n, and between brackets, it's between 0 to,
so this is 3,
3,
and this is
okay.
and this is 4. So
okay.
n equals 4 in this case because this is n minus 1, right? Well, but if I was wrong, I wanted to know. Well, let's say we miss number 2. Well, the only option we have here is this one. So basically, if we miss the value I, this has to be the identity before I, and from I included onwards, it must be a shift by 1. I mean, you have to add 1, right? And this map, in this case, I would call it d supra 2 because 2 is the number we are skipping. Of course, if I were very strict, I should put some n somewhere in the notation because we also have a d supra 2 between, let's say, 500 and 501, for example. But I'll drop the ends from the notation and hope all goes well. Okay. So these are all the injective order preserving maps between these two guys. There are other arrows, but these are all the injective ones. And dually, now fix an n which can be 0. And so I have exactly n plus 1 possible values of I, which are these ones up to n, right? And so, okay, dually, let's say we want to focus on the surjections, at the order preserving surjections from this guy to this guy. And here, there must be, again, because this has exactly one more element than this, and there must be exactly one repeated value. All values are realized because of the surjectivity I'm asking, but there must be exactly one which is realized twice. And so let's say that n equals 3, and okay, and so let's say, because I like the number 2, and let's say again, now I want to map 2 guys to 2, and the rest of the fibers have only one element. Okay, again, this kind of map I would call S supra 2 in this case. And again, there's some ambiguity which I won't care about, but because of I should put the n somewhere, but I don't care. And okay, it is characterized by being the order preserving surjective map from here to here that repeats the value 2, or if you think about it, it's equivalent to saying that it is non-increasing at 2. That means to say that if we call it f, I mean, an f is non-increasing at some I if this happens, right? And the condition can be only stated about an I which is not the last one, because we are considering the next. So the values at which some f can be non-increasing, if the domain is, I don't know, k, are from 0 to k minus 1. And in this case, they are from 0 to n, right? So this other form, this other way to see what's happening here will also be useful later. Okay, so, and these are again all the possible, I mean, in this case we have S0, S1, S2, S3, and not S4, because the possible points at which I can have non-increasing conditions are these. These are all the surjective order preserving maps between any ordinal and the previous one, any finite ordinal and the previous one. Okay. And these are very important because we'll see in a moment that they generate all these arrows, in the sense that all these arrows can be presented as a composition of these guys. And if you ask for certain conditions on what order you compose them, there is a unique composition. But before doing that, let's say now I have an arbitrary order preserving function between two of these guys. Let's call it f. And let's say I want to factor it as a order preserving surjection into some m prime, and followed by an order preserving injection, right? Well, there's a unique way to do this because, well, first m prime. Suppose I have a factorization like this. M prime. I mean, the image of f must be the image of this, and because this is a surjection, it must be the image of this, which I'll give them names. And because this is an so the cardinality of the image of f must equal the cardinality of the image of h, because they are the same image. And because of the injectivity, this must equal the cardinality of m prime, which is m prime plus 1. So m prime is completely determined by who f is. So there's only one option here. And so let's say that, okay, I'm basically the image then will have m prime plus 1 elements, and say let's call them a0 to a m prime, right? These are m prime plus 1 elements. So let's say that these are the guys in the image of f or of h, which is the same. And let's say they are ordered in the right order. Okay, then okay, here I have 0 to n prime, and I want to produce these guys. And the only option I have, if this h is to be going to be order preserving, is to map each I into a sub I, right? So the image is the same. So h is also completely determined, and G must be basically composing f co-restricted to its image with the inverse of h co-restricted to its image, which goes from here, from these sets, from the image sets to n prime. And since it is an inverse of an order preserving guy, it is also order preserving. So G is order preserving, and in fact you can see quite clearly that if a J is mapped to some a sub I, let's say a sub I of J, then in order for this to commute, basically here J must go to I sub I of J, right? So then H maps it to this guy. This is H. So there's only one option, and this option works. So the composition exists and is unique. And now let's say we encounter in the wild an order preserving surjection like this one between some ordinal m and some other ordinal m prime. So here we can say, well, let's consider all the values at which G is non-increasing. So how many of these are there? Well, since this is a surjection, this cannot have more elements than this. So we have this condition basically, or with a plus 1 on both sides, which we can cancel. And what was I saying? Yeah, you can, yeah, I was saying how many points are there here at which G must be non-increasing, and basically it must be it must equal the number of extra points this has compared to this, and this is basically this, right? The extra sizes has relative to this, or this is a plus, this cancel, and this is this. So we have n minus m prime points, extra points here. So there must be exactly n minus m prime points at which G is non-increasing. Let's call them I1, no, J1 to Jn minus m prime. Okay, and if you think about it in your homes, I won't do this because, but it's better to convince yourself by drawing some examples like I did earlier. Basically, I assert that G will be this composition of degeneracies. I start by the last one. and then compose all the way to the one indexed by J1. Okay, this, and if you believe that this is true, then under this condition, this decomposition must be unique because you can read off what the J's are basically by checking which are the points at which G doesn't increase, right? And dually, if we have, let's say, an injection from M prime to M, I mean, this is in general, I've just borrowed the notation from here because then I want to apply it to this case again. But we have any injection, order preserving, of course, between M prime and N, or between these two ordinals. And you can ask, well, again, for this to be an injection, N has to be, no, sorry, this will be N. Okay, M has to be at least as big as this one. So we have this condition. And how many extra points will it have? Well, again, it will be M plus 1 minus M prime plus 1, which is basically this subtraction. Okay, this is the number of extra points. So this is the number of values which are expected to be missed by such H. So let's say the missed values are I1 and to IM minus M prime in the correct order. And again, I state that such an H will be, you can express it as composing these phase maps. I don't know if I mentioned this. I think I mentioned it in passing, but I write it here for you to see. Can this be seen from the camera? Okay. These are the degeneracies. Okay. Now, yeah. And in this case, I will start with the first one and then go to the last one. And again, you can check this in your minds or afterwards or in your homes, or just believe me. But again, if you believe that this is the case, then this subject to this condition, this kind of factorization of a order preserving injective map must be unique because again, you can read off these I's by looking at what's the complement of the image, basically.
When you say unique,
yeah, the factorization, I mean that if you have any factorization,
I give an example. You take the dimorphism from N to 0.
From N to and this uniqueness of here, example, yeah,
from N to 0.
Yeah,
you can compose in any way you want the size. You mean the
what?
S1 composed.
No, that's only one such map. This is true, because all has to go to 0, of course. But among here, any way you compose them will be.
Let's say,
so here you, in this special case, you have
1 to 0, or
yeah,
from 2 to 0.
Yeah,
from 2 to 0. You can make.
Yeah, of course you can. For example, from 2 to 1, there are two options. One is this one.
Yeah,
and one here there's only one option, right? And the other I will draw it here.
So I know, yeah.
So in this case, there are.
What do you mean by uniqueness?
But here in this case, you have uniqueness among a larger. No. What I no. I mean the following. I stated in a rigorous fashion.
Is 1 is 0 or 0 is 1?
No, it should be in order.
In increasing order, yeah.
Okay.
I mean, subject to this condition, but yeah. But in your case isn't a counterexample anyway, because in this case you get uniqueness even without this condition. No, right, it is a counterexample. Yeah. Sorry. No, yeah, it is a counterexample. Yeah. If I didn't ask for this condition, right? But I asked this to be in increasing order, and this as well. But here I compose it in this order, and here I compose it, right? So yes, it's uniqueness among the tuples which satisfy these requirements. That's a good observation. Okay. Yeah. This is a I was about to I was going to do that, but I want to call it that way. When I mean, this is the special case of surjections and injections, and now I will derive a stronger conclusion which applies to any f, right? And yeah, this is like a canonical form, which was what I wanted to get at when I said to understand better what these maps were. So now suppose you have f, you decompose it in this unique way, you decompose your h in this fashion and your g in this fashion, then you write this f equals h and before you did g, and this equals this. Note one thing, that the values, if this g comes from here, then the values at which, I mean the j's, which are the values at which g is non-increasing, because I mean these are precisely the values at which f is non-increasing, because basically because this is in an injection, right? One inclusion is obvious and the other is given by the injectivity of this. And dually, if you have the missed images, which are the i's, the values which are not in the image of h, if h comes from here, then this is also the same as because this is a surjection, right? So this is also the complement of this image, of the image of f. So you can describe this. You have this factorization. Here it, yeah, j1 to j jn minus n prime, okay, which is unique subject to these two requirements, right? No, well, why is this the case? Well, because if you have any other factorization of this fashion, since all of these are surjective, the composition is surjective, and this composition is injective because all of these are injective. So this gives a composition of this form. So by the uniqueness of the composition, this whole lot must be G, and the whole lot must be H, right? Okay, and the uniqueness of these cases gives the general uniqueness. And again, as I said, you can read off the i's and the j's from the non-increasing points of f, which are coincide with those of g, as I said, and from the missed values of f, which coincide with those of h, as I said, right? So is everything clear up now? Yeah. Yeah.
Could you have what happens if you commute the s and the
Yes, I was going to say, well, I mean, this is like a canonical form, but basically, and what this is telling me in particular is that, as I claimed earlier, but hadn't proved, but I have proved now, is that all maps are combinations of the d's and s's, and they are unique when you compose the s first and the d first, and the superindices or supraindices, I don't know how to say, are satisfy these orderings. But now I want to see what happens with the malformed compositions in some sense. For example, which are the informed compositions? Well, it suffices to consider what happens with ill-formed composition. Oh, what? Yeah, for example, well, or if you put two s's in the wrong order or two d's in the, these are the three cases I want to consider. So, for example, the right order for the d's would be the increasing order. That is to say, this would not be ill-formed. This would be, I mean, its own canonical presentation if I was smaller than j. So let's say that this doesn't happen, so that I is greater or equal than j. Then, well, again, you can check it in your homes, but anyone which familiar with singular homology has already done this calculation at some point in their lives. This will give this expression. And note that this condition means that I plus 1 is strictly greater than j. So this is, or what's the same, j is strictly less than I plus 1. So this is the canonical way of writing this. And well, and this is whenever this happens, right? Which is the ill-formed cases. Let's say, okay. And what about the ill-formed S compositions? So in this case, I want to go, well, this will be right. This will be all right. I mean, it will be its own canonical presentation when I is greater than J, right? So when the ill-formed counterpart is when I is less or equal to J, right? And in this case, I get Sj plus 1 and Si. And again, this is the canonical presentation of this. And as Willie said, we also have to consider the case where there is one S and one D, but they are composed in the wrong order. So first you have a D and then you have an S. And all these cases have to be considered because all of them are, I mean, no matter how the E and the J are ordered, but the order of these guys influences the result in the following way. If I is less than J, you get this. If I equals J or I equals J plus 1, you get the identity of wherever you are. And if I is strictly greater than J, then you get Sj composed to the elements. These are all routine verifications, which I leave to the listener or to your act of faith in me. Well, so once you have these relations, you can say and this can be stated in a precise and a rigorous fashion, that this is actually the free category of this with these objects and these morphisms, which are only names now, subject to these relations. And I mean, and these relations tell you how to put any composition of these and S's into this kind of format. And of course, you can compose them by concatenating and then redoing the canonical, the conversion to the canonical format, right? So, okay, so this is basically the simplex category. Okay, and a simplicial set can be described by basically as, well, can I erase this? Is it all right? Okay. I keep this. So I was saying a simplicial set is basically a contravariant functor from the simplex category to the category of sets, and more generally, a simplicial object in some category C is a contravariant functor from this category, the simplex category, to the category C of interest. But in this talk, we will be mainly concerned with the case of sets, of simplicial sets. Okay. So as I said, basically I can say the category of simplicial sets is the functor category from the opposite category of this to sets, that is to say, the functor category of contravariant functor. Let's see. Yeah, I forgot to mention. I won't go into detail but here you have in the simplex category you have some sort of canonical involution, which is given by fixing each object, but in your mind you are reordering internally you're switching to the opposite order on each ordinal, and now each function with what it did to points earlier, now the points have different names, so the functions will have different names, and this defines an involution in the category. Basically, if you had some f from n to m, now this when you apply this involution, it will again go from n to m, but what will it do to some I? Well, this is the new label, but the old label was, so let's say this is the new label. The old label, of course, yes, was n minus I, and f sent it to this is old label, and f sent it to f of n minus I, but that's the name it got in the old nomenclature. So this is the old label again. So to switch to the new label, we have to consider m minus n minus this guy, which is f of n minus I, right? And you can check that this is functorial. It's a very easy computations. What? Well, the point of this is that this involution, when we precompose with this involution in the category of simplicial sets, this gives us a way of also taking like the opposite simplicial sets in some sense. And since we are going to model infinity categories on simplicial sets, I think.
Like the arrows pointing the other way.
Yeah, because basically, no, I mean, the arrows point in the same way because basically they are telling you how these arrows point in the same way, but basically they are telling you how, for example, I mean, perhaps this will be clearer when I give some examples of simplicial sets and particularly the nerve of a category, which is the way you see a category of simplicial set in some way.
If you make a picture,
yeah,
for instance, you have maps from 2 to 0, but you can add a point from 2 to 1.
Yeah.
Let's say add a point on the right, on the very right. Yeah.
Here?
Point, yeah, not so much, at the level of 1. So, so if you, yeah, 1 point.
Yeah.
Justo ahí donde estabas, a la altura del 1, elegí uno de los dos. ¿Cuál dibujo elegí? ¿La flecha de arriba o la flecha de abajo?
No entendí.
Ahí tenés una flecha del 2 al 0. ¿no?
Ah, so which is
Bueno, hacer una flecha del 2 al 1, agregándole un puntito, un 1 nomás.
For the canonical presentation, you mean?
No. I want to understand the evolution. Make it.
Yeah. Okay.
2 to 1.
Okay. Basically, okay. Yeah. I understood. Now, so if this is what Marco is asking, if I understand him correctly, is that if f is this, what is f with check?
If you put,
for example, so this, yeah.
And a mirror horizontally, and maybe.
Yeah, probably this will work.
The evolution.
I think it's probably this. It should be this, right? But let's compute it because I'm quite dumb. So in this case, so f of 0 will be, I mean, here n equals 2 and m equals 1, right? And for applying this formula. So and f will send 0 to m minus f of 0, which is 1 minus f of 0, and f of 0 was 0, so this is 1, right? So 0 goes to 1. Let's do it downward like you suggested. So, no, yeah, what I have in mind actually is this. You just switch the labels. 0 will go.
And now it's the same map.
0 goes to, no, what? 0 cannot go to 1 because so I did something wrong, I think. No, yeah, of f of, not f of 0, but f of n minus 0, which is 2 minus 0, so f of 2, right? Is this right? So f of 2 was 1, so 1 minus 1, and this goes to 0. So yeah, this is 1. So 0 goes to 0, right? Then f of 1 will be m, which is 1 minus f of 2 minus 1, so f of 1. And yeah, f of 1 is 0, so this is 0, so you get 1 minus 0, which is 1, so 1 goes to 1, right? Notice that this isn't how I would generally draw a map, but since I'm kind of, I draw the 0 and the 0, for example, at the same level, and here I am not. But it's for this process to be better understood.
Yeah. Now I wonder why you put 2, 1, 0, and then you put 0, 1, 2, and not 2, 1, 0 again.
0, 1, 2. I'm just what this process does is it relabels this.
Yeah, so you relay, if you relay, you put the same map.
No, but now it's a different map. If I
Yeah, but-
wrote the
but
so
I wonder
yeah.
why you are making a picture.
Yeah, this is a non-canonical picture, let's say, and it is not a picture of this format. Now I will convert it to the ordinary format. So now I will again.
F of 2 is already preserving us, so f of 2 is 1.
F of 2 is 1, yeah, of course.
When I say if
and
you
yes,
picture,
the canonical picture should be 0 goes to 0, 1 goes to 1, and 2 goes to 1. This is the okay.
no,
You,
both
no, this
2
is
and 1
no
goes to 1.
2. Yeah, sorry, 2 and 1 goes to 1. Yeah. Now, yeah.
Okay,
So this is the F check. If this is F.
okay,
Sorry for the mess.
the upside down mirror.
Yeah, you in some way, yeah. You
Yeah,
basically.
Precisely. If you put the new labels, you keep your picture, and
Yeah.
instead of writing 0, 1, 2, you write 0,
Yeah.
1, 2, and the same on the other one.
Yeah, and then I convert to this
and
format.
This give you not the picture but the values of
Yeah.
the new.
Yeah.
Okay, and you make the mirror, and you make and you have the picture of the reality.
Yeah. Yeah, but why we care about this? I mean, this perhaps will be more clear afterwards.
That something like DI check is DI plus 1, where I plus 1 is to be taken also.
Sorry. So DI check you say is equals what?
Dn
To
minus
the
R,
DI
exactly
plus
like that.
1.
Yeah, I think so. Yeah, because for example, in this case, this was in this case, this was an S, right? This is S0, and this is the S1. So the S0 check is S1, right? Yeah. So does that make sense?
Yeah, it's like Sn minus 0.
Yeah, because the possible values for this would be 0 and 1, and you switch them.
Yeah.
All right. If you had for example, from 0 to 5, the S0 check would be S5, and
But
S1 check would be S4, etc. And these also what?
the canonical form, you miss the canonical form, right? When you take check.
When I take the check, yeah, because basically the order is now the wrong order here, right? And here as well. Yeah, assuming that what Willie said is correct, which I believe it is. I mean that the S.
I did the picture.
No, but
It's
yeah.
a triangle. And
Well, I yeah.
look at the on the page.
Okay. Yeah. Okay. So, but at any rate, this involution gives you an involution here, which is basically precomposing, right? It was this. No, it was this. Okay. So, what are some examples of simplicial sets? But okay. Before giving examples, note that this category has very good properties because it's basically a category of presheaves. So, for example, it is, since set is complete and co-complete, this means that the punctual category will again be complete and co-complete, and that you can compute limits and co-limits pointwise. If I knew what a topos is, I would say it is a topos, but since I don't know, I will just say this, and then I prove that it is Cartesian close later if I have time. Well, okay. So yeah, examples of simplicial sets. Yeah, this is like an abstract way of viewing a simplicial set. Now, given this kind of generators or relations view of the simplex category, you can more pedestrian definition of a simplicial set would be just saying, well, we have different sets, one for each non-negative integers, which would correspond like this. So let's say we have a simplicial set in this in this under this definition, which is basically a functor from here to here. This is our simplicial set, and so on these guys, it has certain values which are sets, which for the moment let's write them like this. And well, basically you will have phases and degeneracy maps which go in the opposite directions. So you take this, I will denote with a subindex, and I will do the same for the degeneracies. And basically now you have that this goes from, I mean, if the supra I went from n-1 to n, then this will go from x of n to x of n-1, which under this notation is a map from here to here, right? And dually, this will be a map from here to here, right? Okay, basically, then you specify some sets and some maps which satisfy these relations, but on the other way, because we are now these are contravariant functors on which when you apply x on both sides, the orders are switched because of the contravariance. And basically now you ask for this to happen. So this is like a pedestrian definition of a simplicial set, if you want. And this equals d is 1 identity and sub I. Yeah, the functor on the identity is identity, of course. So this is, sorry, this is a j, and this is on the -1. So I equals j or j plus 1. Right. So basically, a pedestrian view of simplicial set is one set for each non-negative integer, and maps like this with these domains and codomains that satisfy these relations. You can view it as in that way as well. And more generally, in any category, you can specify objects and arrows in that category with the analogous domains and codomains which satisfy these relations. So that's also a pedestrian view of a simplicial object in an arbitrary category, which would be a contravariant functor to the to the category C you are interested in. Okay, now I will give finally some examples of simplicial sets. So the first example, when you want a contravariant functor with values in sets, the first thing that you will want to try is the contravariant functor. So basically, you will fix, let's say, some object n, and you define this functor, which is contravariant, and goes it takes values in sets. I mean, in general, this will denote that in a category C, I use this kind of notation for the set of arrows in C from these two between these two objects in this order, right? So these are the order preserving maps from a blank space to the objects I have I had fixed. And when you replace here the different objects, this gives you a simplicial set. That is, yeah. And this guy I'll denote it by like this, delta supra n. And this, well, and a heuristic way, like this pedestrian view of simplicial sets, basically says that morally you can think of a simplicial sets like a sort of left module over this opposite category, or right module over this category. And the objects of these x sub n's are called simplices, and the n's to which they belong are called their degree or their dimension, right? So basically you have a set which is stratified because it has guys of different degrees, and you can get from some guy of 1 degree to I mean, yeah, you can act on these guys with morphisms of this category. Yeah, so in this case, yeah, this equals this. So the simplicial sets on level n, what on this notation I would call this, I mean the n simplices of this guy are basically the arrows between n and n in the simplex category, and there we have a distinguished one, which is the identity of n. So, and this generates the simplicial sets in, so let's call it iota, no, yeah, it's iota, right? Iota sub n. Huh? So this generates all the simplicial sets, because you can, I mean, any other object will belong to some, I mean, some simplex of dimension k will be in general some simplex here, I mean some element of here. So, and if you think of them as of it as an order preserving function, this is basically, let's call it f. You have some f here, and f equals the identity precomposed with f, right? The identity of n precomposed with f, right? And precomposition is what this guy does on the arrows, right? The contravariant on functor. So this is basically this functor acting on f, and this acting on identity, right? And yeah, in the pedestrian view, instead, if I have an arbitrary simplicial set x, instead of writing, so say we have some simplex sigma, instead of writing it's what you get when you act on it by f like this, I can simply write like this, right? So in this, with this notation, this would simply correspond to f acting on this iota sub n, right? And this is the only f which will work, because when you calculate this, you get f. So only itself will work to express express this arbitrary element as someone acting on this canonical simplex, right? So this simplex it's like it freely generates this simplicial sets, this representative of the. Okay, and yeah, and now if I have an arbitrary simplicial set, what are the maps from this the maps of simplicial sets between this guy and an arbitrary simplicial set? Well, this is basically the functor represented by n, and this is an arbitrary functor. So by the Yoneda lemma, this amounts to choosing an element of here, right? Basically, any morphism from this contravariant, from this preheaf to this one, will be, from this simplicial set to this one, will be a natural transformation. Let's call it alpha, and this alpha has its component at n will be someone who goes from from this guy to this guy, right? So, and here you have the identity, and here you want to see what it maps to, and the Yoneda lemma says that I mean, when you vary the alpha, you get all the possible values, and this is a bijective correspondence, right? So, but the correspondence is given by evaluating this at J sub n, let's say, right? So when you want to understand what the I mean, to give a simplex of degree n in an arbitrary simplicial set X is the same as giving a map from simplicial sets from this guy to X, right? From the standard n simplex to X, right? Yeah, yeah, and these maps you can also, I mean, if you have someone, I'll erase some things in order to avoid confusion. So suppose I have yeah, some function from k to n. Since it is order increasing, it can be viewed as a k tuple. Let's say I know a0 to, well, when I say k tuple, I mean it starting at 0 because this guy starts at 0 to ak, and all this living in, I mean, all of these guys live here, right? So these are basically the images of the function you chose. So you can represent a function like this by an ordered tuple, and basically under this correspondence, this iota would iota sub n would be basically numbering 0, 1, etc. up to n, right? And it is interesting to compute. Yeah.
You say the morphism between those simplicial sets K and N.
No, K and N are not simplicial sets. They are elements of the objects of the simplex category. Yeah. So this,
the maps between the order preserving maps between K and N you represent as a tuple.
yeah. So instead, I enumerate. I mean, instead of, so the tuple would basically be f of 0, f of 1, f of 2, etc. up to f of k. That's the tuple basically, and it is increasing. It cannot have you can have 2 or more guys which are the same consecutive, but you never decrease, right? Because the function is order preserving. So you can represent him like that. And if you do so, if you make this identification, you can ask where, well, how do the phases and degeneracy, I mean, what do the actions of the yeah, basically you will get that okay, acting with the sub I on this, this will be basically precomposing this as a function, like with this guy, right? Because again, this is what actually, if you want to be very pedantic, you can. It is this functor acting on this thing, but this functor is just mapping each guy here to precomposing by that guy. So basically, you get precomposing by this to this function. I'm identifying functions with tuples, as I said, and this is basically this function precomposed with the supra y, and this supra y was someone which went from k supra y goes from k minus 1 to k, right? And if you so, and this a0 to ak is some function, and these are its values in increasing order. This is some function to n, right? There's some object here. This is my f. I am making this identification. So precomposing with this map basically skips I. So it remembered it was the identity before I. So before I would get first this, but then it added 1. So this will go to this, right? And yeah, and this will go to basically you delete I, right? And if you do the same calculation with the degeneracies, it will give you that you repeat well in the ith place, you put twice that value, and then you desplazar, ¿cómo se dice? Yeah, no, desplazar. You shift the rest to one place to the right. So this is these simplicial sets. You can in a more as concretely as possible. It would be, I mean, a concrete description would be all the tuples of guys of tuples of any length at all, but with all members of the tuple, all elements of the tuple are between 0 and n, and they are and each tuple is non-decreasing, right? And the faces and the degeneracies act by deleting and repeating respectively, right? And we are interested in this guy because, well, first, as I said, it's the first one the first kind of simplicial sets you will think about. If you think about the presheaf, you first look for the representable ones, which are these, and because also we have this correspondence between maps which go from Okay, and now another example. In this pedestrian view of simplicial sets as sort of modules over this opposite category, you can, I mean, like stratify sets with these actions of the faces and the degeneracy. You can say, well, I can define a notion of simplicial subset of a simplicial set, which is basically a subset of these, and which is closed under this action, right? And this would just, of course, you can also define it as in the functor language, but perhaps for thinking about it, it is more convenient in some places. So, for example, one simplicial subset of this guy is what I would call its boundary, but this is just suggestive notation for now. This is the set of all f all maps in this category with codomain the ordinal n, which are not surjective. Right? So, and of course, those with degree k correspond to the maps from the ordinal k to the ordinal n, which are not surjective, etc. And so basically, if we think of these, so these guys are a subcollection of these guys. If we think of them as tuples, they would be the tuples such that you not all of the elements between 0 and n appear on the tuple, right? And since at least one guy is missing from the image of f, or from the tuple if you want to see it as a tuple, then you can factor it through the through some the supra I, right? So you can always say f is the supra I of some f prime, right? So and if we think of this, okay, and this is basically the supra I. Well, sorry. Okay, okay. This can also be described as the union of the images of these under the supra I put forward I 0 to n of these guys, right? So this is a natural transformation between the on functor corresponding to n-1 and the functor and this one, right? And I mean, this is the natural transformation, which is the image in the Ioannidis embedding of this. Okay, and is it evident that this equals this?
I mean, you should say what the union means.
No, okay.
You want to use the other whiteboard?
What?
You want to use that whiteboard?
Yeah. Yeah. It's kind of a mess. Sorry, but
I mean, you
Yeah.
can also say,
it's you can say it as a colimit. Yeah.
you can say, you just take the simplices up to, you just take the simplicial set in this case, right?
Yeah.
I look at the xi from 0 to n minus 1.
Xi or Si.
Yeah,
Yeah,
x is delta x. Right?
Okay.
You take all the xi with I going from 0 to n minus 1. Right?
Okay.
Okay. And now there will be, you take from there, some of the simplices in x will be degenerate. Right?
Well, I haven't defined what the degenerate simply is.
Yeah, the image is
The
a
image.
basic.
Now the image is the usual.
And then you just chop off the upper thing and take all the everything that generates. You take all the s's, and that's it. That's
Yeah, that's basic. You can also describe it as the
skeleton.
sorry.
That's the n minus 1 skeleton.
Yeah, it's the n. Yeah, when you consider
Which is essentially what you're doing there. You take the
but you don't chop off everything that is above. You own but what remains is what is generated by what was already down there, right?
yeah.
For example,
Yeah.
you chop off,
and then you add.
you add the general things which ought to be there. Okay, yeah, and you also have well, you can also view this.
As you say, you're right. This element it should be understood as correct.
But now I'm confused because
You haven't yet defined a simplicial subset, have you? So this is so
The-
far just the-
Yeah, in the pedestrian view, I
but
have.
he didn't write it.
uh,
He said it's a subset.
so it's a collection of subsets which are close under the actions of these guys and with the same actions, right? But you can you can also define it as some other functor which admits a natural transformation, all whose components are inclusions, right? I mean a natural transformation to this one. Okay, and you also have the horns here, which so. But I kept thinking about. I mean, if yeah.
Maybe we'll say this later, but you have a simplicial complex, not a set.
Yeah.
Which you can draw.
Yeah, I will.
Let's say the standard simplex. Then you can associate a simplicial set.
Yeah.
The boundary is precisely the boundary in the
Yeah.
sense you can draw.
Yeah. Yeah, that's right. But anyway, there's no much distance between the two descriptions. I mean, they are what you get when you consider the simplices generated not by all of the not by all the simplices of here at once. You always keep at least one one vertex without no, I mean unused. So it is also it's you can think of it as a simplicial subset generated by d sub I of iota sub n with I from 0 to n, right? Which would be like the faces, right? Is this correct? I mean, this is the one generated by these guys.
Yeah.
Yeah. Well, and the horns, I mean, the horn is a simplicial subset of this guy, and of course, then particularly of this one. And there's one for each I between 0 and n. And the ith horn is, well, if you want to think of this as a colimit, it is the same union morally, but well, let's say here J, we use J, but you delete you don't in the union you don't consider the ith guy. So basically, it would be the simplicial subset of the standards and simplex generated by these, but with J not equal to I. So basically, it is the union of morally, it is the union of all the faces except the ith one, right? That's the horn. So if you want to draw some pictures, for example, if you have the standard 2 simplex, the boundary is this, and for example, let's say this is actually here I have 3 1 simplices. Then I have 3 0 simplices, that is simplices of dimension 0 or degree 0. Then I have 3 1 simplices. Then I have 2 simplex here, but I also have the degenerate 2 simplex. Well, I have, prior to that, I forgot, you also have the degenerate 1 simplexes, which are, for example, a 1 simplex which lives all here, which would be the tuple 0 0 if you want. That's why they are called degenerate. And you also have all the degenerate. Well, here I didn't say what degenerate is, but it's basically those which are in the images of the degeneracies, right? And if you think of them as tuples, you quickly see that they are basically the tuples which have repeated guys. And the standard simplex is such that it has only non-degenerate elements up to dimension n, but then all the rest. I mean, if the dimension of a simplex is bigger than n, then it must be degenerate, because if you view it as a tuple by the pigeonhole principle, even not viewing it as a tuple, if you see it as a function, then again by the pigeonhole principle, that must be repeated values. So these are all degenerate. Yeah, they are the non-injective functions, if you want to view it as functions. Okay, there's lots of equivalent descriptions, but intuitively, I hope it is clear what these are. Okay, but I was describing what. Okay, so you have the degenerate 1 simplices, and you also have the degenerate 2 simplices, for example, one which lives entirely here or one which lives entirely here, etc. And then, well, you have the only non-degenerate 2 simplex, which is iota 2 here, and then you have all degenerates, all the higher simplices, for example, a 3 simplex which lives here or here or here. They are all degenerate. And well, this would correspond to the boundary. And for example, the 0th horn, I mean the 0th face is the one opposite to the vertex 0. So the 0th horn would be just this. And if you want to draw a 3-dimensional picture, and then, for example, the 0th horn would be the boundary of the tetrahedron without this face, right? So it is like megaphone, how to say? Yeah, or like or a cone in some sense. Yeah. How do you say cucurucho? Does any of you know?
Ice cream cone.
Ice cream cone. In Spanish, it's better. Well, yeah, these are some standard simplicial sets, and these horns are important. I haven't written what the horn is, but yeah, basically it's the union in the sense of a colimit. But if you think of these as graded sets, it's literally the union. I mean, right?
If you,
yeah.
I like pictures. So,
yeah, it's me too.
These are they talk the pictures, but I like also the fonts or so on. But I'm always confused when one talk about one thing doing a picture and talking about a picture doing the other. So for instance, you make a picture of a two simplex, the boundary and one of its horns. And
actually I've only drawn the non-degenerate simplices, and the degenerate ones are the ones generated by these.
you draw also the points of the so, but if you want to define the simplicial set for each n, you have to give a set.
Yeah, it's basically the set of
So
faces. So
this is-
this, for example, there's no point in asking what's this, for example. That's when you later I'll talk about the geometric realization, but yeah, for now it's just the sets are the set of simplices. So for example, in degree 0 there would be this simplex. I mean,
So in degree 0 is the map going everything to 0, everything to 1, everything to 2. So it's a map from 2 to 2, isn't it?
No.
The two parts.
The maps go the other way. From 0 to 8.
So this is a simplicial set, isn't it?
yeah.
So in degree 2,
Yeah, in
there must
degree
be a
0
set.
it's
and
this
the
guy.
set is the set of map in the simplicial category from 2 to 2.
Yeah.
So
Those are everything too. Those are the degenerates.
and whose image is 0 and 1 or 0 2.
Yeah, 001 or 011.
Is
These are the
boundary.
these are in the boundary. I mean, the boundary has two simplices in it, but they are only the degenerate ones.
There is only one non-degenerate.
So at degree n,
Yeah.
right? Yeah, the iota sub 2 in this case.
And so in the horn is the map that the image only contains 0 and 2 or 0 and 1, but do not contains 2 and 1.
The definition I have here is, if you want, it's the image with along with I is properly contained in n, in this case in 0, 1, 2, right? So the image of your function, if you want to think of this as a tuple, it would be what's inside the tuple. This cannot be everything but I, right? Or it cannot be everything and also I. Right. So if you have I you can have I, which is 0, but if you have I, you cannot have all the others. For example, you cannot have this, the iota sub n wouldn't qualify because the image of iota sub n is all of this. So in particular, when you unite this is, in this case it's unnecessary, but when you unite this, you get all of the ordinal and
So
not.
you cannot have everything but I. That explains that if you
but-
have
but-
0 horn, you cannot
Yeah.
have 2
You-
and 1. in
Yeah,
the
you
image.
cannot have 2 and 1 because in the 0 horn, when you unite 0, you get all, right? So that's the definition of the function or tuple level or way of looking at it. Okay, and these simplices and horns, you can use them to well, you can also ask, giving a map of simplicial sets from the standard simplex to X is the same as giving an n simplex. So you could ask, for example, what does it mean to give a map from the boundary to Xn, sorry, to X, and basically it's equivalent to giving giving a map in simplicial sets from the boundary to some X is the same as giving some simplices, which I will call like this, which are all in X of Xn minus 1, which would be the images of these guys, like of the faces, right? And you ask them to satisfy certain compatibility conditions, which come from the fact that when you do the boundary of one of these, which is n minus 2 simplex, and you do another boundary of another of these, sometimes they coincide. So, and the condition translates to basically to ask for this to be but this comes from the fact that this is a colimit of these guys, right?
Is that I less than J? Or
Yeah,
something?
sorry, I forgot what was I? Yeah, with for every I less than J. And giving a map, well, if I put here the ith horn instead of the boundary, it's the same condition, so except that the ith guy is not considered, right? So you have this condition and this condition whenever J and I are not I, right? I and J, well, let's say J1 and J2. J1 less than J2, right. These, well, whenever these are different from I, in the case we are coming from the ith horn, right? And so this description can, why do we care about it? Well, because there are some sets, some simplicial sets can satisfy some sort of lifting condition, basically, which basically says that if you, for example, if the so-called can condition says that if you have a map from any horn to X, it can be filled. That is, you can give a map from all of the yeah, from all of the simplex, right? Oh no, yeah, right. No, but I want.
You have
yeah.
5 minutes.
Well,
but
okay,
if you talk in the air.
okay.
Same time.
What do you prefer me to erase next? Perhaps this. Yeah. So I wanted to, well, if I have only 5 minutes left, I want to mention two more examples of simplicial sets, which well, for the next time, if it's okay, I will give the second part in which, or perhaps other person can give it as you wish. But the idea was to construct these examples as particular instance of a general construction which produces functors valued in simplicial sets, and also produces adjoints to those functors, an example of which is the geometric realization. So, but since I don't have time for this, I will just give two more examples. Well, one example is the classical one from singular homology. When you compute the singular, well, when you define the singular homology of some space, so let's say you have a space X. Let's write something before Willy kills me. A space X, and you consider all of the. No, okay. I'll define this as the standard n simplex. It's just a symbol. It's suggestive, but you shouldn't think of like applying. For the moment, it's not applying some functor to the other simplex. It's just a thing on its own, and it's the convex hull in. I mean, this is the convex hull of E0 to yeah, and basically
is for each n simplex the convex hull.
No, I was just saying who this guy is, and you have a functor f which goes from the simplex category to top, right? Which is to each n simplex. Sorry, sorry, for each n it gives the it gives this guy. It gives this guy, and if you have an order preserving function, this gives the some affine map, particularly a continuous map, which is induced by, so let's call it f between bars, right? So if you have this functor, you can consider the same functor but from the opposite category, and you can post compose it with the with this functor, which is contravariant, so it goes from the opposite category of top to set, right? So basically this is top of like if this functor is called f, so or I could call it like this for the moment. Okay, it's basically let's call it f. Sorry. No, sync is the one you get. Now sync is this composition.
Yeah.
Right. So, but yeah, this is this basically. So this is a simplicial set called sync of x, and basically given an n simplex here is basically a continuous function from the standard topological n simplex to the space, and when then you can consider what the phases and degeneracies look like, and they basically are, well, you're more interested in the phases in the case of singular homology. The phases are basically restriction to one phase, and the degeneracies are copying the I mean, they produce the same image, but they come from they are parameterized by a higher dimensional simplex, and they are all clashed together. And well, in the case of, well, so if now you vary x, you can I mean, if you have a map from x to y, you get a map from sync x to sync y, which is basically post composing with your map. And that's the natural transformation on each component. And finally, if you have a category, you can construct what's called its nerve. And here here, if you believe that, here what I did basically was I considered, in this case, in the case top, in the case of sync, I had some functor from this to top, and then I defined this. Here goes some n, right? But n varies. So this is the sync functor, right? To each x, it gives this guy. Right? So, and I can copy this kind of construction, and well, this gives a functor from which I call, in this case, sync, but generally it gives a functor from top to simplicial sets, and I can mimic this construction. If instead of top I consider cat, I can the category of small categories, and each n simplex, sorry, each ordinal n, I map it to the poset 0, 1, 2 to n viewed as a category. So basically,
itself.
Yeah, what?
You map it to itself.
Yeah, and well, an order preserving an order preserving function here induces a functor from this to this, because I mean it's a thin category, so all you have to check is that, I mean, factoriality in this case corresponds precisely to the order preserving condition, right? And if you do the same here, basically you get another functor, which is, so if you use this f now, so what does it mean to give a functor from this set? I mean, a morphism here, which is a functor from this category into another category. It means picking a chain of n composable arrows in the codomain category, and if you check what the phases and degeneracies look like, well, the degeneracy, the ith degeneracy is basically in the ith place you put the identity of I, and the faces, the inner faces, that is those which correspond to I equal to 0 or to n respectively, they are just deleting the first and the last arrow respectively. And so sorry, those are the outer face maps, and the inner ones in the ith place you have 2 arrows and you get 1 by composing them basically. So you and this construction, this basically gives you, if you do this, then you get a map from the categories. I mean, basically doing the same construction, you get a map from the category of small categories to simplicial sets, and with a little work you can, well, and this is called the nerve functor, and with a little work you can see that that it is fully faithful, I think, right? So and you can, in fact, you can characterize what the image of the nerve functor is, that is, which simplicial sets come from are the nerves of small categories, basically by the thing I was going to mention earlier, and I will mention in the next talk if there is one, which is the thumb lifting condition with uniqueness. Sorry for not covering all of it. If you agree, I mean, I have no problem.
These last part you should say.
I think you should explain this nerve construction.
These are very important.
Yeah, but my plan was to mention them in passing at first, and then to mention it I mean, because I ended up describing the general recipe I would use to construct functors from your favorite category C to the simplicial sets, which is given a functor from the simplex category to your favorite category. And I also describe a recipe for, well, in the case that when your favorite category happens to be co-complete, that it's, say, it has all small colimits, then you can get adjoints to, I think they are right adjoints to these, right? Adjoint to what? Realization. Isn't that the adjoint to sing?
Well,
the adjoint to this one.
yeah.
The nerve also has an adjoint, but I haven't found any concrete any concrete what?
Categorization.
Categorization. Okay, I'm a little deaf. Well.
Di cuenta de que tendría que ponerlo
Muchas gracias.